Welcome back, everybody. This is Lecture 16, Part 2, the Bohr Model of the Atom and Emission Spectroscopy. If you're wondering why I look the same as I did at the end of the last lecture, it's because it's only been 10 minutes. It's still Friday night here in North Seattle, and I hope you're all still doing well out there. So I'm going to start you off with a video, this time from Bozeman Science from Dr. Anderson, who will talk with us about the Bohr Model, which should be familiar to you, and if you're not, hopefully this helps. And as well, he's going to talk about how the Bohr model helps us account for how and why it is that atoms can emit light, emission spectroscopy. So I'm going to take you to Bozeman Science and to Dr. Anderson for a video on the Bohr model. And this time I'm going to try to successfully embed it within this actual video.
Hi, it's Mr. Anderson, and this is AP Physics Essential Video 4. It's on the atom. In the last video, we talked about how Ernest Rutherford and his gold foil experiment had helped scientists discover this positive small nucleus in the center of an atom. But that didn't tell us what the electrons were doing. And he just speculated that they were moving around the nucleus almost like planets in orbit around the sun. But one of the researchers working underneath Rutherford, Niels Bohr, spotted a problem in this. He knew that any charged particle that's moving is going to be giving off electromagnetic radiation. As it does that, it's losing some of that energy, and so it's going to quickly spiral into the middle and annihilate essentially the whole atom. So he knew that wasn't right. He also knew that as it gives off radiation, the wavelength of that radiation is going to vary. And as it varies, we're going to get this nice, smooth spectrum of electromagnetic radiation given off by high-energy atoms. But when we started to look into space, what we found is that light wasn't smooth. It had these discrete units within it. And so that spectra had to be described. And Bohr's model helped to do that. And so if you think of it like this, and this works for hydrogen, is what the Bohr model is built on. You have these energy levels. And so an electron can be in energy level 1, energy level 2, energy level 3, but it can never be found in the middle. It's quantized. It has to be in one of those levels or another level. And so how does it move between levels? Well, if it absorbs energy from a photon, electromagnetic radiation, for example, it'll jump to a higher level. And as it moves down, it's going to emit those photons. And that helped to describe what we were seeing in the spectra. And so that improved our model. So we now had the cloud that had the electrons in it, and then the nucleus. And so we found these negative electrons in the cloud, and then protons and neutrons were found in the nucleus. And in a neutral atom, the number of protons and electrons are going to be equal. And the electrons tell us a lot about the properties of that atom. In fact, the whole periodic table is built on the electrons. Electrons especially we have in these outer levels. Now, the Bohr model helps us explain what those electrons are doing and how they're moving. They move into these discrete energy states, and that helps us to explain the spectra. And so if you look at any kind of an atom on the periodic table, the atomic number 2 tells us the number of protons we have. And so we're going to have these positive protons that are going to be found in the nucleus. We can kind of figure out how many neutrons roughly we're going to have in an average atom by taking the mass number, subtracting the atomic number, and so we would know in helium, for example, that we're going to have 2 neutrons. Now, since the number of protons and electrons are the same in a neutral atom, we can figure out that we've got these electrons moving around the outside. And the number of electrons that we have out there tell us a lot about the properties of the atom. And so if you look at the periodic table, this whole thing is essentially built on the number of electrons that we have, because that tells us a lot about the properties. And so if you look right here, we'll find copper, silver, and gold, which are all very similar, are in the same column. And that essentially says that they have similar outer level electrons. Or if we look in the first column, all of these are highly reactive, all the noble gases are not, and so the properties of atoms are built on those electrons. But there were problems with this planetary model. Electrons weren't orbiting like planets. They were actually jumping between orbits, according to Niels Bohr. And so they didn't just move back and forth on all these infinite number of orbits around the nucleus, giving off a smooth amount of spectrum, almost like a ladder, that an electron could be here, but it could also be here, and it could never be found in the middle. We call that being quantized. It has to be in a specific unit to exist. Now, how do you move an electron to a farther level? Well, you have to put a little bit of energy into it. So if we add a lot of energy, we could jump it up to this energy level. And as it falls back down, it's going to release a certain amount of energy. And so this is a visual or a model of what the Bohr model might look like. And so as it orbits around the center, if it receives a photon, it jumps to a higher level. If it gives off an equal photon, it'll drop down to a lower level. And so it's only existing in these quantized orbits. And this helped to explain spectra, because before the model was discovered or was put forth, people had started discovering spectra. They were looking into space, not with just a prism, but a spectroscope. So they were splitting the light into all of its different wavelengths, and they were starting to see these lines. So when you're looking at the sun, for example, which is mostly hydrogen, we saw these different series. So the Lyman series was developed by one scientist who was using spectroscopy, and he came up with an equation that explained what was going on, but you couldn't see this spectra because it was into ultraviolet. We also saw the Passion series that was showing the similar relationship, but this was in the infrared, and the Balmer series was seeing the same thing. And so what really he was explaining, let's throw the Balmer series up here, is that they were seeing these discrete units of light. And so where was that light coming from? If you look at hydrogen, well, you can see here as we move from this energy level 2 up to energy level 3, it requires a certain amount of energy. And as the electron falls back down, it's going to give off that energy. It's going to give off that light. And so the Bohr model predicted what these numbers were, and they fit perfectly with the numbers that we were seeing in the spectra. And so again, this only works for hydrogen, and so it's a good step model, or it's a good model to get you started on understanding how the atom is really put together. But did you learn the energy level structure of an electron in an atom at the appropriate scale being investigated? In this case, it's at these energy levels in hydrogen atom. I hope so. That's the Bohr model, and I hope that was helpful.
All right, hopefully you enjoyed that video. I just spent 45 minutes finished filming this lecture, realized my mic was muted the whole time. It had been muted during the video to not get the reverb, so life's about making mistakes and learning from them. Anyways, here I am once again. Maybe the second time is a charm. So I'd like to talk with you about some of the key points that was brought up in that video, some of these postulates that Bohr came up with that Dr. Anderson talked a bit about. The first of those, highlighted here in yellow, is that the hydrogen atom has only certain allowed energy levels. He kept talking about this, these states in which electrons can exist, these quantized states. Electrons can't have any amount of energy. They can only have certain quantized energy states. We'll talk more about that later on as we get into the quantum model and why that is. Each of these states corresponds to a circular electron orbit of a fixed size. And for now, that's okay to think about, that these electrons are moving in a circular orbital pattern, and the further away from the nucleus the electron is, the more energy it has. When we get to the quantum model, we'll realize that the electrons do not move in a fixed circular orbit. For now, it's okay to think that. The larger the orbit, which I just mentioned, the greater the energy associated with it. And no other orbits existed in the atom except for these 7, in the case of hydrogen's Bohr model, 7 energy levels. Each allowed energy state, Bohr gave an integer number to, called n. We'll call that the principal energy level later when we get to the quantum model, that Bohr called a quantum number, that ranged from 1 to infinity, but realistically for atoms only gets to the 7th or 8th energy level, after which, if the electron were any further away from the nucleus than that or had any higher energy state, the attractive force between the electron and the nucleus would be too weak, the electron would leave, and the atom would be ionized. The lowest energy state, the smallest orbit, the closest to the nucleus that electrons can be allowed, is called their ground state, and that's n equals 1. The higher up that electrons are, the more energy they have, the higher the integer, n equals 2, 3, 4, 5, 6, 7. If an electron is in a higher energy state than their ground state, if they're further away from the nucleus than they can otherwise be, they're in what's called an excited state. And that's only possible if the atom absorbs the right amount or a quanta of energy. Postulate 2, as long as an electron moved in an allowed orbit or stationary state, the electron, and therefore the atom, did not radiate or absorb energy. So while electrons are moving at the speed of light around an atom, as they're doing so, they are not emitting or absorbing energy. It's only when they fall from a higher to a lower energy state that they emit or absorb as they rise energy states. Lastly, the electron can only move from one allowed orbit to another if it absorbs or emits an amount of energy exactly equal to the energy difference between the two orbits, the change in energy. This meant that the hydrogen atom could only change from one stationary energy state to another, and could therefore also, like I've said a few times, only absorb or emit specific or certain amounts or quantas of energy. So this diagram is depicting an electron, let's say in a hydrogen atom, falling from the third energy level to the second. In the third energy level, it would be in an excited state because a hydrogen atom in its ground state has its electron in the first energy level. So it's falling from the third to the second, and as it does so, it's releasing a specific amount of energy that corresponds with a particular wavelength, frequency, and color of light, which we'll talk about. And this equation, which is the very small amount of math in this unit, we'll talk about as well today, which says the change in energy, or the energy associated with light, or a photon of light, is equal to Planck's constant h times the wavelength v. And again, I'll talk with you about that in a moment. Here we see the emission spectra for 3 different atoms, hydrogen, mercury, and neon. Hydrogen has 4 spectral bands: purple, blue, green, and orange, which we'll talk about in a moment as we look at a diagram like we saw in the video with the Lyman, Balmer, and Paschen series. Hydrogen has only 4 visible spectral bands. Mercury and neon, on the other hand, have far more. And that's because the energy transitions that mercury and neon's electrons can undergo happen to have energy amounts associated with more wavelengths of light that can be seen by our eyes. The energy amounts, as the electrons fall, happen to, in mercury and neon, fall more so within the visible spectrum. More of hydrogen's energy releases as electrons fall are in the infrared and ultraviolet. So please know that different atoms emit different numbers of colors of light and different colors of light based on the energy transitions their electrons can undergo. So we saw a diagram like this in the video. This is the number of or different transitions that the one electron in a hydrogen atom can undergo. I'd like to remind you that hydrogen's one and only electron is in the first energy level. That is when it's in its ground state. And if it were given the right amount of energy, that electron could transition to an excited state, to the second or third or fourth or fifth or sixth energy state. In that excited state, the second, third, fourth, fifth, or sixth energy state, the electron can fall back down to any of those lower energy levels. From the sixth, it could fall to the fifth, right? It could fall from 6 to 5, it could fall from 6 to 4, 6 to 3, 6 to 2, or 6 to 1. So too can it fall from 5 to 4, 5 to 3, 5 to 2, 5 to 1, and so on and so forth. Lots of different energy transitions electrons can undergo. They need not always fall to their ground state. They could fall to another lower excited state. In hydrogen, and it's so nice that there's a nice pattern to hydrogen. In hydrogen, any time an electron falls to the first energy level, 2 to 1, 3 to 1, 4 to 1, 5 to 1, or 6 to 1, the energy transition, the energy that's released, is so great that it falls out of the visible spectrum. It's ultraviolet light. Ultraviolet literally mean higher in energy than violet, violet light being the highest energy visible light. And that's over here. It's called the Lyman series. Any transition to the first energy level is so great that the light emitted is ultraviolet. This diagram on the right depicts well the fact that the further away from the nucleus that we get, the closer together the energy levels are. The smaller the difference between the energy states that electrons have in higher energy levels. The first energy level in hydrogen is so close to the nucleus, is at such a low energy state that once again, any drop to 1 releases enough energy that it's outside the visible spectrum. Any drop to 2, however, 6 to 2, 5 to 2, 4 to 2, or 3 to 2, for hydrogen only, emits a color / wavelength / frequency of light that happens to fall within the visible spectrum. These 4 drops, 6-2, 5-2, 4-2, 3-2, correspond to the 4 spectral bands we saw on hydrogen's emission spectra a bit ago. That drop from 6 to 2, which is greater than 5-2, 4-2, or 3-2, emits the most energy, and that's the purple light that we see for hydrogen, purple light having more energy than the other colors. The drop from 3 to 2, for example, which emits the least energy, is the red band we see from hydrogen, red light having less energy than purple light in the visible spectrum. We'll talk more about these values for these wavelengths here, but these represent the wavelengths in nanometers, nano meaning 10 to the minus 9. The more energy there is in light, the higher the frequency, but the lesser the wavelength. So this wavelength of light that is purple has a lower wavelength than this wavelength, which is greater. Finally, any drop to 3 emits so little energy that it is also outside the visible spectrum and is in the infrared spectrum. So any drop to 3 emits infrared, and in fact any drop to 4 or 5 also emits infrared. So that's a little bit about the options for energy transitions in a hydrogen atom and the colors of light or the types of light that are emitted in those different transitions. So the last thing I'm going to do with you, as I said a moment ago, is a little bit of math. We're going to look at that equation, E or delta E equals HV, and see how that allows us to do some more cool things with emission spectra and math. First thing I'd like to do is define some variables, some of the variables that are going to show up in these two equations I'm about to publish for you. All right, one of those variables is abbreviated with the lowercase letter c, which is the speed of light. The speed of light is abbreviated with a lowercase letter c. Any type of light, any color of light, any wavelength of light, any frequency of light, gamma rays, ultraviolet light, infrared, visible light, has the same speed. The speed of light is constant, and it's 3.0 times 10 to the 8 meters per second. Extremely fast. C stands for the speed of light. A V, but really it's a symbol, Greek symbol whose name I forgot. It's really this little guy, is the abbreviation for frequency. Frequency, in general, describes how often an event happens. And in the case of light, it is the number of waves per second. It's the number of complete waves that pass a stationary point in a second. Its unit as such is waves per second, but because we know we're talking about waves, it's just 1 over seconds, or seconds to the minus 1. The unit for frequency, abbreviated with a V, it's not technically a V, but we say it is 1 over seconds, or seconds to the minus 1, and it really means waves per second. We just leave the waves out. Lambda, the Greek symbol lambda, which is right there, is the symbol for wavelength, and it describes the length of a wave, the length from trough to trough, or, I don't draw very well, from crest to crest. It's the wavelength. So that would be lambda. Light has a very short wavelength, at least the visible and infrared and ultraviolet light. Radio waves, for example, which is a type of light, have wavelengths that are sometimes a mile long, which is crazy. But visible light has a very short wavelength. And while the unit for wavelength is in meters and needs to be plugged into these equations as meters, oftentimes light's wavelength is given in nanometers because the wavelengths are so short, and it gives us nicer, bigger numbers. And I want to remind you that nano is 10 to the minus 9. So a nanometer is 10 to the minus 9 meters. Lambda stands for wavelength. The unit for wavelength is meters, and nanometers is 10 to the minus 9 meters. E will stand for energy. Energy, we know, is measured in joules. And then lastly, this letter H is the abbreviation we use for Planck's constant. Max Planck, who was one of the pioneers of quantum theory, worked with Einstein, came up with this constant, and it's 6.626 times 10 to the minus 34 joules times seconds. 6.626 times 10 to the minus 4 joules times seconds. It's an awkward constant. It's extremely small. It defines the smallest length possible, a Planck length. More on that later, but there it is, 6.626 times 10 to the minus 34 joules times seconds. Those are our variables. I'll give you the equations we're going to use next. The first of those, and it's not crucial you understand how these equations work and why they do, you're certainly welcome to ask me about it, is that the speed of light, c, which has a unit of meters per second, is equal to wavelength times frequency. C is equal to wavelength times frequency. And if we look at that from a unit perspective, it should make sense. Speed, we know, is in meters per second. Wavelength is in meters. Frequency is in 1 over seconds. So meters times 1 over seconds will give us meters per second. C equals wavelength times frequency. The speed of light is the wavelength times the frequency. So that's one of the equations to write down or pay attention to. The other one is E equals h nu. I just remembered it's nu. E equals h nu, or E, energy, equals Planck's constant times the frequency of light. That is maybe one of the 10 most fundamental equations that I feel like I've learned about in all of science. It comes up all the time. Don't worry about understanding where it comes from. Trust that it works. If we look at that from a unit perspective, we know the unit for energy is in joules. Planck's constant a moment ago we heard is joules times seconds. And frequency is 1 over second. So if you multiply joules times seconds by 1 over seconds, the seconds cancels, and of course we're left with joules. So there are the two equations that we want to pay attention to as we solve a couple problems together. All right, the question is, what is the wavelength of light that has a frequency of 1.4 times 10 to the 12 seconds to the minus 1, which could also be thought of as 1 over seconds or waves per second. Well, if we're going between wavelength and frequency, we want to use that speed of light equation, which says that c, or the wavelength, is equal to lambda, c, the speed of light, is equal to lambda wavelength times nu frequency. We're looking for frequency here, so we could isolate the frequency by itself and say that the speed of light over lambda is equal to the frequency. The speed of light is a constant. It's 3.0 times 10 to the 8 meters per second. In this case, the frequency is 1.4, and I don't know if you noticed that we're solving for wavelength, not frequency, so it should be wavelength is the speed of light over the frequency. So speed of light is still 3 times 10 to the 8 meters per second. The frequency is 1.4 times 10 to the 12 seconds to the minus 1. And when I go to my calculator, I get 2.1 times 10 to the minus 4 meters. The seconds canceling, leaving me with the unit for wavelength I would expect, meters. All right, let's try one more. So this one says to calculate the energy in a photon of light with a frequency of 4.26 times 10 to the 14 seconds to the minus 1. Oh, by the way, seconds to the minus 1 are also called hertz. A hertz is an inverse second, or a 1 over second. All right, energy, frequency. Looks like we're going to have to use that E equals h nu, or equals hv equation. H, remember, is a constant, Planck's constant. So that is 6.626 times 10 to the minus 34 joules times seconds. Did I mention that's my favorite constant? Times 4.26 times 10 to the 14 hertz, or seconds to the minus 1. Of course, seconds will cancel. We should get joules out of this, and we go to our calculator, we get 2.82 times 10 to the minus 19 joules, with 3 significant figures due to the frequency having had only 3. All right, one more problem before we wrap this lecture up, and it's going to be review question 10 out of your book on page 282. This is a great little problem. So question 10 says to calculate the energy released when an excited hydrogen electron returns from n equals 5 to n equals 2. All right, and I copied and pasted the diagram out of our book that would allow us to do this. We need to know what either the wavelength or the frequency of light is in a transition from n equals 5 to n equals 6. So there's the, n equals 5 to n equals 2. So there's the n equals 5 line, and it looks like a drop from n equals 5 to n equals 2 emits a wavelength of light that is 434 nanometers. But we need to calculate the energy, and we know that energy can be calculated by Planck's constant times frequency. So the first thing we need to do is convert this wavelength into a frequency, and then plug that frequency into E equals hv to find the energy. So I'm going to start with my speed of light equation. I'll go to green. Speed of light is equal to wavelength times frequency. The speed of light is 3 times 10 to the 8 meters per second. The wavelength is 434 nanometers. Remember that nano means 10 to the minus 9, so we're going to go 434 times 10 to the minus 9 meters times the frequency, times x. So I divide by 434 times 10 to the minus 9, and that's going to be the frequency, and when I go to my calculator, the frequency will be 6.91 times 10 to the 14 1 over seconds, or hertz. But that's not the final answer, that's the frequency. We now want to figure out how much energy is in that frequency of light. So E equals h nu, 6.626 times 10 to the minus 34 joules times seconds, times the frequency we just got, 6.91 times 10 to the 14 inverse seconds. Seconds cancel, we're left with joules, and the final answer is 4.57 times 10 to the 19 is our final answer. That is a wrap, folks. Lecture 16, Part 2, the Bohr Model and Emission Spectra, has come to a close. Enjoy whatever it is you've got in front of you today, and life is hard work, but I'd argue it's worth it all. Have a great day.